Next, we'll take a look at a certain fairly simple class of sequences, the periodic sequences. And we're also going to talk about periodic functions because it's very similar. So let's start with sequences. What is a periodic sequence? So let U be a sequence of, let's say, numbers. Can be reals, can be complex numbers. Actually, it can be a sequence of anything. And it should be an infinite sequence. This is a situation where finite sequences are actually more complicated. A positive integer d is said to be a period of U if each I in n satisfies ui equals ui plus d. Now I see I should have started the sequence at 0 so that actually I in n makes sense to apply ui to. Anyway, this is what it means to be a period. You will see a bunch of examples. A sequence, the sequence U is said to be periodic if it has a period. And finally, let d be a positive integer. The sequence U is said to be d-periodic if d is a period of U. What are examples of periodic sequences? Well, first of all, an infinite sequence U is one periodic if and only if we take this definition and we apply it to z equals 1. So each I in n satisfies ui is ui plus 1. So what does this mean? U1 is U2, sorry, U0 is U1, U1 is U2, U2 is U3, and so on. So in other words, all the entries are equal. So one periodic sequences just have the form A for some object A. That's not very interesting. An infinite sequence U is two period, so it has the form A for some A. Next, what does it mean to be two periodic? It means that it has the form AB, 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 and so on for some A and B. And the A and B can be equal, so a one periodic sequence will be two periodic in particular. The standard example of a two periodic sequence is the powers of -1. So -1, -1, 1, -1, 1, -1, and so on. This is two periodic. Here is a sequence that's not periodic at all. You can also call this the powers of 0, because 0 to the 0 is 1, but 0 to the everything else is 0. It is not periodic. Because if it's periodic, then each entry must appear infinitely many times, but 1 appears only once. There is more examples. See the notes for that. I should just mention one little example that's just neat. Not very consequential, but neat. Let's take the Fibonacci sequence and change the sign. So let's define a sequence of integers by recursively by we begin with 0 and with 1 as for the Fibonacci's, but then instead of the Fibonacci recurrence, gn is gn minus 1 plus gn minus 2, we make this plus a minus. Should be kind of the same, right? So here are the first few values. Okay, how many values do we want to find? Well, let's do it. Every next value is the last one minus the second to last one. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 1 is minus 1. Minus 1 minus 0 is minus 1. Minus 1 minus minus 1 is 0. 0 minus minus 1 is 1. And so on. What you see here Well, first of all, there aren't that many values in total. More interestingly, they seem to return after, so they seem to repeat every 6 steps. This is a copy of this, and if you go further, you get another copy, and so on. So, and by the way, this is not g of n, this is gn. So we observe that the sequence here is 6 periodic. It has period 6. And you can even describe the values explicitly using the Iverson bracket. This is all easy to prove. Once you have found the pattern, you just induct on n, strong induction to be precise. But it's a nice little thing. So we took the Fibonacci numbers, which are definitely not periodic. They keep growing and growing. We changed the little sign, and we got this little degenerate sequence, which has just 3 different values. So what can we say about periodic sequences? Here's a bunch of properties. Let U be an infinite sequence. Then, if A and B are 2 periods of U, then A plus B is a period of U. Secondly, if A and B are 2 periods of U, and if we have A bigger than B, then A minus B is a period of U. So periods can be added and subtracted, subject only to the requirement that periods have to be positive integers. By the way, you can, of course, define periods that are not positive integers in the same way, but of course, then you have to say that the sequence is periodic if it has a positive period, which is, to me, looks like too much work. C, if A is a period of U, then NA is a period of U for any positive integer n. D, if A and B are 2 periods of U, then GCD AB is a period of U. This is interesting. So if, for example, 3 and 5 are periods, then 1 is a period because GCD of 3, 5 is 1, which, as you know, means that all the entries are the same. And finally, if A is a period of U, and if P and Q are 2 non-negative integers such that P is congruent to Q mod A, then UP is UQ. We will not prove this in detail. See the notes for a detailed proof. Parts A, B, C, and E are fairly straightforward. As to part D, let A and B be 2 periods of U. Nice little argument. Recall that there exist 2 positive integers, x and y, such that GCD of AB is xa minus yb by an exercise on homework set 1. Yes, we're going to use it now. So consider this x and y. Now, so part C is saying any positive multiple of a period is a period. Since A is a period, this means that XA is a period. So part C shows that XA is a period, since A is a period, and similarly that YB is a period, since B is a period. And every time when I say period, I mean period of U. Now, the difference must also be a period because part B is saying the difference of 2 periods is a period. So XA minus YB is a period because it's positive, because it's the GCD. So since XA minus YB is a GCD, this means that the GCD is a period. So part D is proved. And as a corollary, periodic sequences have, well, if you have a periodic sequence, it has periods. at least one. And so it has a minimum period, the smallest period. So let M be the smallest period of U. Then the claim is that all the other, so all periods of U are just the positive multiples of M. For the proof, here is again a sketch. It's detailed in the notes. For now, how do we prove the two sets are equal? Well, they're equal if each of them is a subset of the other. So we must prove that the first is a subset of the second, and the second is a subset of the first. So how do we prove that the first is a subset of the second? Let A be a period of U. We must show that A is a positive multiple of M. How do we do it? Well, A and M both are periods of U. So part D of the previous theorem shows that GCD of AM is a period of U. But since M is the smallest period of U, this entails that the GCD is at least M, because M is the smallest period of U, so any period of U is at least M, and GCD is a period of U, so this is at least M. Now, it's a GCD, so it's a divisor of M. How can a divisor of M be at least M? It can be this in only one situation, when it's exactly M. So the only divisor of M that is at least M is M itself. And therefore, M is the GCD of M, and so it's a divisor of A. In other words, A is a multiple of M. And of course, it's positive because it's a period. So we have showed that A is a positive multiple of M. As to the second claim, so that every positive multiple of M is a period of U, this simply follows from part C of the previous theorem. Because M is a period of U, and part C says that any multiple of a period is a period. So any multiple of M is a period. So much for periodic sequences. You will see them a bit in the exercises, but let us now switch to something else. And see the notes for how parts of the above theorem fail if you switch to finite sequences. Just as a little aside, for example, this part fails, this part fails. Other part stays, so these parts are still valid, but that's pretty simple. So now let us change our topic from sequences to functions.